Good morning. I'm Yoichiro Dobashi from Japan. Now I worked as an engineer of civil engineering field in Tokyo after my graduation. Today it's an honor to introduce this topic. My presentation title is this. And in this study, we conducted the intercomparison of some physical ocean models and global ocean bottom pressure data, which is installed for the purpose of detecting tectonic activities. It's included in Frontiers in Earth Science. So let's start the contents. Firstly, my motivation of this work is here. Better understanding of ocean bottom pressure fluctuations sharing timescale with cluster deformation. Practically, there are some methods that are already applied to detect tectonic activities, and there are some assumptions like that spatial scales of earthquake sweeps are mostly shorter than those of oceanic variations. For example, differencing nearby site from reference site or statistical method. But I think simulating phenomena by numerical ocean model is a so straightforward approach and effective approach to understand the fluctuations. Before discussing ocean models, I listed components of bottom pressure. Observed pressure value is ds/Pb and it includes P reference and delta Pb. P reference is the value reflects referencing pressure level of local site. If the water depth is 1000 meter, gauges records 100,000 hectopascals. And delta P is the pressure anomaly. It deviates from P reference. And Pc is vertical deformation resulted from earthquake. Pt is tide. Amplitude is quite huge, but numerical model can be precisely estimated and be differenced well. PO is non-tidal oceanic variations and estimated by ocean models here, but there is a room would be improved in terms of accuracy. PA comes from atmospheric pressure loading. Please image the storm surge situation. Sea surface reacts to the atmospheric pressure variations quite well and synchronized. It is called inverted barometer effect commonly, but somewhat small gap of that reaction we call non-IB effect fluctuate bottom pressure. The other day, Tonga eruption caused a tsunami event and bottom pressure gauges recorded it as this PA component. PD and residuals are not geophysical components, so we don't comment here. These are the 5 ocean model products which we utilize in this study, and we can divide by 2 types. Single-layer ocean models, barotropic model, developed by co-author Inazu. He tuned for modeling bottom pressure. And multi-layer models, commonly called as ocean general circulation model, OGCMs, and the baroclinic model, which covers the whole ocean. But Jacob 2M is just Japanese local ones. A main external forcing is definitely wind, and heat and freshwater flux, which is considered in all GCMs, is mostly negligible if we focus on the slow slip-like event, because we focus on the event shorter than intraseasonal scales. Here, a single-layer ocean model considered in atmospheric pressure loading. Even I know OGCMs can be considered atmospheric pressure as an external forcing in their formulations, but the data isn't open to users. Here, I show the equation calculating ocean bottom pressure. The OBP is shown as an integrated water pressure from sea bottom to sea surface, including atmospheric pressure loading. In the single-layer ocean model first, model provides sea surface height eta, induced by wind drag force and atmospheric pressure loading at each horizontal grid. So actual OBP at local site is given by pressure due to sea surface height anomaly plus atmospheric pressure loading on sea surface. If inverted barometer response is completely realize ocean bottom pressure fluctuation by atmospheric pressure loading is completely compensated by adding p atom in this process, but there is a gap. So the NIB, non-IB component affects ocean bottom pressure fluctuation in SOM model. In the oceans, we can get OBP by integrating seawater density from bottom to surface with a long-wave hydrostatic approximation. Right picture shows the integrating image. In these models, atmospheric pressure loading isn't considered, as I said, so we don't have to add p atom here, so it is there. In calculating processes, we visually confirmed the compensation relationship between sea surface pressure and subsurface pressure. The OBP is shown as an anomaly from this compensation. Okay, this figure shows a visual image of compensation of sea surface height pressure, and the subsurface pressure is black. And green line describing bottom pressure fluctuation and is produced as byproduct of this compensation. Sea surface height variation is predicted relatively accurate owing to satellite observation or so on. So how to predict this dot line, the subsurface is the key to reproduce OBP well, I think. In the previous slide, I explained the modeled OBP by using equations, and in this slide, I use output time series of SOM, and I will visually explain. SOM is developed by two external forcing, wind force and atmospheric pressure loading, and time step value of sea surface height is output. In this figure, number 1 is wind inducing sea surface changing, and ocean bottom fill it directly because we use single layer model. And number 2 is sea surface height changing induced by atmospheric pressure. If the inverted barometer response is completely realized, the magenta graph and navy graph is just flipped, and ocean bottom doesn't feel that variations. But residual between them, OBPP, is certainly there as a residual of them. Finally, seafloor fills the summation of these components. Of course, we also confirmed the nonlinear effect of this two external force is negligible in this focusing time range. So in this work, we attempted to combine this OBPP with the bottom pressure from OGCMs and evaluated that after. To evaluate models, we compared modeled OBP time series with observation over Pacific Ocean. We used dataset from 6 regions: Hikurangi Trough, Nankai Trough, Japan Trench, Aleutian Trench, Cascadia Subduction Zone, and Chile Trench. And more than 150 sites collected the data whose purpose is detecting seafloor deformation. I think this kind of research of data comparison in globally, which focus on seafloor deformation, is still limited, and this work is kind of the first step, I think. Here I show the example at the Hikurangi Trough where good agreement is found in observation and ocean models. In this region, single layer ocean model perform better than OGCMs, so we added SOMP driven by atmospheric pressure to OGCMs output here. This is the result of wind driven model, glories. The vertical axis is pressure anomaly, and the horizontal axis is time steps. Upper part showed the comparison of observation with glories without the SOMP. Our red line is observations, and the sky blue line is modeled OBP of glories. Each of them are band passed within 3 days to 90 days, and then this black line is the residual after subtracting modeled OBP from observation. If the black line is shaped and RMS becomes smaller, the detectability of earthquake signal become higher. And the lower part showed the comparison of observation with glories with the SOMP added. We see the improving the agreement of observation and modeled OBP here. After adding SOMP, especially in short periodic variations. That is, we can see from power spectra also, which showed the power before and after correction by modeled OBP. The agreement is good at periods less than around 10 days. This result is consistent with previous research related to OBP vibrations induced by atmospheric pressure loading. This is the comparison result in the Aleutian Trench, where the Alaska Amphibious Community Seismic Experiment was conducted. In there, pop-up bottom pressure gauges were deployed. Same as the Hikurangi case, I showed the time series of each model without SOMP and with SOMP. The left map showed the site design of OBP gauges, and this bar shows RMS amplitude before it and after correction is green. Let me get straight to the result. High contrast SOMP performed the best and reduced RMS amplitude 17% from original observation RMS. And the right figure showed the LA26 result, and the RMS amplitude is here before model correction, and each model's results are there. In high comp case, the left is the RMS amplitude and the right is the correlation coefficient without SOMP. And with SOMP, the result is here. We analyzed all data in the same manner and united the result as a bar figure. Shows the RMS amplitude of each region in next slide. In this slide, I will explain the RMS bar graph's meaning using a conclusion slide. Firstly, this gray bar means the RMS amplitude of each region. In this study, we want to reduce the length of this gray bar because it means the background noise level. So far, we applied ocean model to shorten that. In Hikurangi case, this is a Hikurangi case and Nankai Trough, Japan Trench, and so on. Observed RMS here is relatively big. So we applied wind force bottom pressure model firstly, and we can see how much noise level was reduced. And after that, we applied atmospheric pressure loading ocean bottom model secondly. Also, we can check the effectiveness of models. Finally, we get this blue bar as the residual RMS as the proxy of detectability. Smaller signals can be detected if it is short. In this slide, we compare the model results to each other by the same step as the previous slide. Applied wind force bottom pressure, and secondly applied atmospheric pressure loading force pressure. From this result, a single layer ocean model reduced residual RMS of all regions. On the other hand, other oceans can't reduce RMS in Nankai Trough and Japan Trench. Also, result implies the effectiveness of atmospheric pressure loading depends on regions. Okay, this is my final slide. This is the same graph as previous one, and this is the shortest residual RMS bar by the best models of all each regions, and result and future of this work. I think sub-centimeter detection is so difficult by model using approach now, but would be improved well in the future by collaborations of cross-cutting specialists. So thank you for your attention today.